So noise in operational amplifier or any integrated circuits can be divided into four types of different noises. This should be integrated circuit, not integrated circuit. Should be divided into four type of different noises. You have the thermal noise, which is basically your electrons or particles, semiconductor particles, holes and electrons. They are moving randomly, and as temperature increases, their random motion increases, and due to their movement, it produces heat, it produces noise. The higher the value of resistor you're using, more thermal noise is created. So thermal noise is basically directly proportional. Thermal noise is directly proportional to the value of the resistor. Then you have a short noise or Poisson noise, because the distribution of the short noise is the Poisson distribution. And this is due to the random fluctuation of the current, which is basically due to the discrete nature of electrical charges. You have flicker noise, which is also called pink noise. And mainly this noise occurs at low frequencies due to the resistance fluctuation in electronic devices. And it is also called, and that's why it is also called 1 over F noise. That is, it will be more at lower frequencies, 1 over F. Frequency is smaller, noise will be higher. And the last noise is popcorn or burst noise. And basically, when you create a semiconductor, you can have imperfections in the surface of the semiconductor. And then due to those imperfections, your input bias current can momentarily change its value, and when you take the rate of change of that current, that can become substantially high, and it can produce a noise which is called the popcorn noise or burst noise, and generally it is less than 100 hertz. Both the first two noises, thermal noise and short noise, they have Gaussian type distribution. I said Poisson distribution. Both of these have Gaussian type distribution. This is the Poisson function that it's followed, not the distribution, but Poisson function. So both of these have Gaussian distribution, and they fall under white noise or Gaussian noise. Generally, most of you are familiar with white noise. Pink noise, again, like you have white noise, there's also a pink noise, and flicker noise is a pink noise. And if you actually search online for pink noise, you see that they use in different type of therapies and stuff the pink noise, like they do white noise as well. And I found really good resources about these noise from Texas Instrument for their 741 handout. So if you click here, I don't know if it's when I created the link, it is clickable or not. Let's see. Yeah, it is clickable. So if you click here, then it is going to take you to the resource of TI, noise analysis and operational amplifier circuit, and in this you can look at detailed analysis of noise, introduction, different type of noises as we discussed, short noise. There's also an avalanche noise, which is not discussed in your book, but they are discussing it, so you can look at it as well. And we're just gonna keep our discussion of noise up to this level. We're not going into any more detail than this. Just to create the circuit model of the noise, all type of noise, the RMS value of all the noise is expressed as voltage and is referred to the non-inverting input of the circuit. So this is the RMS value of the noise referred to the input. And then what is the output noise voltage due to this input? We calculate using this equation, and observe what do we have here, noise gain. So this noise gain came from the study of noise. So the output voltage, output RMS voltage due to the input RMS noise, which is the cumulative noise in the circuit, is the noise gain times the input RMS noise. Now in your textbook, Appendix C, you have two different graphs that deal with the noise, and they're using one of them, which I also copied over here in example 4.8. So this is total noise referred to the input in microvolt RMS value and the source frequency, and there are three sets of lines here, as you can see, and each represent different band of frequencies. So 10 to 1 kilohertz, 10 to 10 kilohertz, and 10 to 100 kilohertz. So whatever the input source resistance is, because the noise is referred is go back to the input source resistance because you're applying the voltage at the input. So whatever the resistance connected over here at the input, that is considered as input source resistance, and the output noise or the input noise referred is on the y-axis. So in this example, which is example 4.11 from your book, I just copied and pasted over here. Basically, you have a non-inverting amplifier here. You have 1 kilo ohm source resistance connected to the source. This is your source. They are not showing it, but this is your source. And this is a 741 operational amplifier. The range of frequencies over which this operational amplifier is operated is 10 Hertz to 1 kilohertz, and they're asking you what will be the output noise voltage RMS value. So you're going to apply the equation Vn naught equals Kn Vn input, and first you're going to observe V in input for this frequency band with the source resistance of 1 kilo ohm. So you're going to go to 1 kilo ohm right here. You're going to go to the frequency band right here, and you will observe that the value is 1 microvolt RMS. 1 microvolt RMS. And then you're going to go ahead and figure out what is the value of noise gain. For both inverting and non-inverting amplifier, as we discussed, the noise gain is 1 over Rf over R1 or Ri, whatever you want to call it. So 100K over 100 ohm, which will be 1000. So 1000 plus 1, 1001. So Kn is 1001. 1001 times 1 microvolt is 1 millivolt. So the output RMS value due to the input noise is 1 millivolt.